about praxis. So his first question was, how do we get around Shor's algorithm? Will, I think this is for you.
Sure. I'll preface this by saying that I am not a cryptographer, so I'm sure our cryptographer will chew me apart for something I'm about to say, but I'm happy to answer it at the level that I'm familiar with. So Shor's algorithm is, it's a good question, and Shor's algorithm is particularly important or relevant to us because it drives a lot of the decision-making behind the protocols used in the Praxis network. Shor's algorithm basically breaks in sufficiently sized quantum computers. It'll break the large prime integer factorization problem and also the discrete log problem. So a lot of the signature mechanisms and encryption mechanisms or protocols that we're familiar with, RSA, ECDSA, DSA, using Shor's algorithm in a sufficiently large quantum computer, these will all be broken nearly immediately once and if this quantum computer appears. The way that we've addressed Shor's algorithm is that we don't use either the integer factorization problem, or we don't rely on the integer factorization problem, or the discrete log problem. We use hash-based signatures, which hash functions are based on pseudorandomness, and so just by design, these signatures are fundamentally resistant to Shor's algorithm. One thing that is important to keep in mind is there are ways to actually weaken hash-based cryptography using quantum computers. This is what's known as Grover's algorithm. I mentioned this in the chat. And there's actually a third mechanism, which is not reliant on quantum computers, called the birthday paradox or the birthday problem. And that's particularly important because it can be combined with Grover's algorithm to weaken the strength of hash functions. What this means at a high level is that you need to choose hash functions that are sufficient length to keep your security. So when I say security, you might say a security level is 2 to the n, which is basically how long it takes to brute force attack in a particular encryption scheme or hash to try to find a collision. Technically, I think you would want something like 2 to the 100 to be fairly confident that something is secure against brute force attacks. By using something like Grover in combination with the birthday paradox, I think what you end up with is, according to literature, if I remember correctly, a 1/3 reduction, or a reduction to 1/3 of the classical security level. So if it was 2 to the 100, it would now be reduced down to 2 to the 33rd, which is obviously a massive reduction. So all it means is that you need to basically increase the size of your hash function to accommodate that. So instead of 2 to the 100, you would use 2 to the 300, and that would give you a 2 to the 100 classical security level. So that's basically what we've done here to mitigate the attacks that are known against hash-based functions via quantum computers. We just make sure that we have hash outputs that are large enough to withstand even quantum computing protocols.
This isn't just a theoretical thing. And if people who are node operators will know, about 2 months ago, I think we pushed an update which increased the size of primes in the payload for CMIX to 4K primes, which means an individual message, because of how we combine them, is about 8,000 bits long. Part of the reason for this is to ensure that large enough hashes can be used by Praxis. So this